G'day, Dustin here. We are in the southern end of the Chesapeake Bay here on the east coast of the United States, and behind me is Navy Station Norfolk. This is home to the US Navy's Atlantic Fleet, and it's the largest naval station in the world. It's spread across about 3,600 acres. That's about 2,500 football fields or about 75,000 statues of owls. Ironically, however, over the last decade or so, the place has been spending more and more time underwater due to more frequent flooding in the area.
Norfolk was hard hit by the storm.
We've got about 8 inches of water.
Floodwaters have started to recede.
Roads are underwater.
And unfortunately, the water now wants access to the bases.
The base routinely floods at high tide.
Now, to be fair, it's not just the Navy base experiencing all this flooding. It's also Norfolk, which is behind us here, and Portsmouth, which is down this way, and the Hampton roads in general have all experienced an increase in flooding over the last decade or so. Before the 1980s, floods occurred on maybe 1 or 2 times a year, but now it's occurring at 1 to 2 times a month. So what's causing all this flooding? What's sending this place the way of Atlantis? Well, that's what we're going to do today. We're going to take a deep dive on understanding what's going on. Now, when I think of flooding, I generally think of storm surge or major rain events, and that certainly happens in this area, but it's not the cause of increased flooding over the last few decades. In fact, moderate to severe storms have not increased in the Chesapeake over the 20th century. Instead, the floods here, and here we are at Portsmouth at the dock, and you can see that it's fairly well covered. Floods here are caused by high tide events. This is why they're sometimes referred to as blue sky flooding. Let's take a look at some data. At the northwest tip of the Navy base is the Sewell Point Tide Station. NOAA has been collecting tide data from here since the late 1920s. Let's look at 1950 and 2020. What we're looking for is anything above this red line. That's our nuisance flood line. Above this means you're going to need some gumboots. In 1950, tides never breached this level, but we fast forward to 2020 and it's a different show. We can see that the mean sea level has shifted up. That's the blue line here, and consequently there are about 25 records greater than that nuisance level. We also see that the flooding is clustered, which is to be expected. Sticking with Sewell Point, we can plot the monthly average sea level data between 1950 and 2020, and again the trend here is really clear. Sea level, or more specifically relative sea level, has been creeping up at an average of 4.7 millimetres per year, and recent data shows that this rate has actually increased. That equates to more than 1.5 feet of relative sea level rise over the last century. Looking to other tide gauges in the region show similarly high rates of relative sea level rise, and in fact, this region has experienced some of the highest rates of relative sea level rise on the US East Coast. So our level 1 answer to what's causing an increase in flooding over the last decade is that relative sea level in the area has risen. You've probably heard that climate change causes sea levels to rise, but to be more accurate, that's really referring to absolute sea level, or kind of the height of the ocean above, say, the centre of the Earth, which is not entirely accurate, but for this level it'll do fine. It's the volume of the ocean. For instance, when the ocean's warm, the warming causes the water to expand, and this in turn raises absolute sea level. Conversely, during periods of glaciation, so these are cold periods, water still evaporates off the ocean like normal. However, rather than making its way back to the sea, it gets locked up in ice sheets, and this in turn causes overall sea levels to drop. Now, for people in coastal communities, absolute sea level is not the important parameter. Instead, for them, the issue is relative sea level. Relative sea level is affected by both absolute sea level, so the height of the ocean, but also by how much the land changes in height. All right, so let's unpack that a little. And what we want to keep an eye on here are the red lines on the measuring sticks, the relative sea level and the absolute sea level. So let's imagine we have some land ice melting. This will, of course, increase absolute sea level. And if that's all there was to it, we would also see an increase in relative sea level. But there are also various forces that affect land height. And so if land height is increasing more rapidly than absolute sea level is increasing, then we'll see an overall drop in relative sea level. We see this happening in Alaska, where even though absolute sea level is on the increase, the land is moving up at a greater rate, and so relative sea level is dropping. In Norfolk, it's the reverse. Absolute sea level in the area has been rising at about 1.8 millimetres per year, but land here is sinking. More technically, it's subsiding. And current data suggests that subsidence is occurring at about 3 millimetres per year. This gives us our roughly 4.7 millimetres per year of relative sea level rise. All right, so our level 2 answer is that the increase in flooding that this area has experienced is due to relative sea level rise, but that's mostly due to the ground sinking. Okay, welcome to level 3. This is where things start to get really interesting because we're really getting to the meat of it now. What we want to understand is what are the factors that drive absolute sea level rise and that affect land height. Now, I've already touched on the two big factors that affect absolute sea level rise. That is the melting of ice sheets or land ice and the thermal expansion of water. Nevertheless, let's look at some data. Since 1993, absolute sea level has been increasing on average by 3.3 millimeters per year. Now let's add the ocean mass data, which has also been increasing, predominantly due to the melting of land ice. And here's the thermal expansion data, which again has also increased due to the warming of oceans. We add these data together and we see that they account for much of the increase in absolute sea level change globally. But earlier I said absolute sea level was increasing in this area at 1.8 millimeters per year. So what's going on there? Well, when we look at the sea surface height data, we see that some areas have increased in height more than others. In fact, some appear to have decreased. The 3.3 millimeter per year figure is really just an average for the globe. It's not happening uniformly. Now, to unpack why this happens, let's consider the melting of land ice a little further. The melting of land ice has the direct effect of obviously putting more water into the ocean, but also has a number of indirect effects which can play out at more local scales. First would be the effect on gravitation. So think of Antarctica. There's this massive lump of ice sitting on top of the Antarctic continent. That mass there has a gravitational pull on the water around it. It's just kind of pulling the water in. As the ice sheet melts, the grip of that ice sheet on the surrounding water reduces. It becomes weaker. The gravitational pull becomes weaker. And so the water that was pooling initially around it now redistributes across the globe. Another indirect effect is how the meltwater affects currents. Here on the east coast of the US, there's a big current referred to as the Gulf Stream. In fact, it's the reason why Europe gets much better weather than it really deserves. This current pulls a huge amount of water up the coast. However, recent data has shown that the melting of the Greenland ice sheet is changing the way this current is flowing. It's essentially slowing it down. And that means that there's more water building up to the west of the Gulf Stream, and some estimates put this at 5 to 10 millimeters of sea level rise per year in the local area. Turning our attention to land subsidence now, again there are two big factors at play in this area. First is the removal of groundwater from aquifers. An aquifer is a water permeable rock under the ground, so think of like a sandy gravel or limestone for instance. These are rocks that can hold water, and we can drive a big straw into it and pull that water out and use it for drinking water or whatever else. However, if we're pulling water out at a greater rate than it's recharging, then the new water's going back in, then we're going to reduce the water pressure in that aquifer. Now underground in this area, we have kind of a sandy gravel type component mixed with a clayey silty type component. Now the issue here is as the water is removed from the aquifer, pressure in the aquifer decreases, and so the clayey silt layers collapse, they compress. This leads to an overall slumping in land surface and an increase in relative sea level rise. And the US is certainly no stranger to subsidence caused by the removal of groundwater. In California's San Joaquin Valley, for instance, the ground has sunk by as much as 7 meters in some places. The other big factor affecting land subsidence in this area is glacial isostatic adjustment. So let's unpack those terms. During the last glacial period, about 25,000 years ago, there was a major ice sheet which extended all the way down to about New York. And that ice sheet is pressing down on the crust, and which presses down on the mantle beneath it. Now this mass pushing down on top of the crust of mantle pushes that mantle out in front of the ice sheet. This is called a forebulge, and that's essentially where we are here in Norfolk. This would have been part of that forebulge region. As the ice sheet melts, all that mass is removed, and the mantle then begins to equilibrate. It starts to push back under the crust where it was once depressed, and by doing so, the land that was in the bulge area, which is where Norfolk is, begins to sink back down. This process accounts for about 1 millimeter per year of subsidence in this area, but it's playing out over thousands of years, as opposed to the roughly 2 millimeters per year that the withdrawal of groundwater has contributed to land subsidence. There are some other factors here that could also be affecting ground subsidence. The primary one there being the crater, which is just up here at the southern end of the Chesapeake Bay. About 35 million years ago, a rock about 3 kilometers across slammed into the area. At the time, the sea level was much higher than it currently is, but still it plunged through the sedimentary layers and into the bedrock that's under us. And the remnants of that form a breccia, which is the conglomerated material from the impact itself. Now, there is some speculation that this could have been contributing to subsidence in this area as the breccia itself kind of compacts. However, the data suggests that this has minimal impact, if at all. So our level 3 answer on why the area is experiencing more flooding is because of us, mostly. Relative sea levels have risen, which is mostly due to the land sinking, and the land sinking is primarily due to the fact that we've been pulling water out of it through groundwater extraction. Then of course there's absolute sea level rise and the local effects due to changes in current, and absolute sea level rise is mostly due to the melting of the ice sheets, which we're playing a massive part in through climate change effects. So what does the future hold for Norfolk? Well, kind of more of this behind us. Sea levels will continue to rise in the area, and this is one of the floodgates that stops water from moving into the city of Norfolk itself. It is expected by 2030 that tide-related flooding will have increased by 3 times over the 2010 levels, and by 2050 it'll be 10 times as bad. The Army Corps of Engineers have estimated that by 2100 we could see relative sea level rise by as much as 1.8 metres or about 6 feet. So there are big challenges ahead for the Norfolk region, and in order to meet those challenges it means billions of dollars basically. Now, while the cost of meeting these challenges is of course high, the cost of not doing anything is much higher, and these challenges must be met soon. To paraphrase Chaucer, time and tide wait for no one. The Chrysler Museum behind us here spent about $24 million a decade ago to refurbish their basement, basically moving electrical equipment and air conditioning out of there so that it didn't get flood damaged. This water here is coming through cracks in the pavement. Entangled. Look at this.